Easy. I'm ready. Hey, senior. I will mute you, bruh. Oh, let me even connect so that you know I'm serious.
Are we on?
Yes.
Wait, let me see. Wait. We are on. All right, please. Good afternoon, everyone. Hope you are fine. Papa, must I transition? All right. So, yes, it's a brand new day, and we are coming to continue with our power electronics tutorial. So, kindly follow. And so, we've done everything up to single phase diode bridge rectifiers. Okay, so we are left with three phase diode bridge rectifiers. Then we are left with the how we call it. Left with three phase diode. We also left with thyristors. Then we'll go into the inverters. That's the DC to AC inverters, where we will see the square wave modulation and the pulse width modulation. Okay, and then we'll just solve some number of questions. Let's see now. We saw the single phase diode bridge rectifier as this, right? We saw it as this. We had diode 1, this, yeah. Ow. So this is what we saw. This how it is, right? Then we had a source connected here. Now with the three phase diode bridge rectifier, you add another leg, another diode leg like this. All right. So you have it like this. Then go through your smoothing inductor through to your load like this. All right. So now here, this becomes your diode 1, diode 3, diode 5. This becomes diode 2, diode 6, diode 4. All right. Then you have your three-phase supply here. It's like your, let's say, VAN, phase voltage for B, phase voltage for B, phase A and B, phase voltage for C. Right. So this one connects to this point here. This one is connected to this point here. Finally, this last one is connected to this point here. So initial principles, as we know that if VAN is maximum, if here is maximum compared to the 3, then V1 will supply, right? I'm sure you remember that. Yeah. So let's see. Let's see how this circuit works, okay? Now, this is my V. We know that let's say my VAN, right, is given by what? E sine omega t, right? For three phase, E sine omega t. Then your VBN is given by E sine, three phases like this, A, B, C. So then my VBN is given by E sine omega t minus 2 pi over 3. Then VCN is given by E sine omega t minus, sorry, minus like 240, right? But that is my having plus 2 pi over 3. So these are the phases, which means that my VB, so this is my VAN, right? Then my VBN lags this one by 6 degrees. So my VBN will come like this. Become my VBN. You get it? You get it. Sorry. What? Right. So this become my VBN. Become VBN. Now VCN leads this one by this angle here. 120. So that one comes like this. That one comes like this, which is its maximum here. That's how it goes here. Then it comes down like this. Then it goes up like this. Then it comes down like this again. Yes. Yeah. So these are the waves. Okay. Now pay attention here. When VAN is maximum here, when VAN is maximum, D1 will conduct. So when VAN is maximum here, at this point VAN is maximum. Which means at this point D1 will conduct here. So this is D1. This is D1 here. When VBN is maximum, D3 will conduct. D3 will conduct here. So here, so this region, it's not drawn to scale, but just like from this point to this point, from this point to this point. Then now when VCN is maximum, D5 conduct. I have my D5 here. I have my D5 here. Now when VCN is minimum, when VCN is minimum, D2 conduct. You get it? For the connections to the back, when it's connected to, like, if I have a die like this, okay, like this, and the maximum is connected here, it conducts. If I have it like this, and a minimum is connected here, it conducts. You get it? Sure, because it's about the reverse bias for it to conduct with the back. So now, when AN is maximum, this one conducts. When B is maximum, this one conducts. When C is maximum, this one conducts. Now, when C is most minimum, D2 conducts. So when C is, please no, so it's not brain scope, but like this C, you know that this C here that comes here and gets it. So C will conduct here, and it will be that your D2 that's conducting when C is most minimum. Now, when, let's see here, this A, right? When A is most minimum, D4 will conduct here. This D4, you see, A is connected to 1 and 4. When it's maximum, D1 will conduct. When it's minimum, D4 will conduct. When it's minimum, D4 will conduct here. At this point, D4 is conducting here. Then now, this is B. When B is minimum, B is connected to 3 and 6. When B is maximum, D3 is conducting. When B is minimum, D6 is conducting. So here I'm having D6 like this. So that's it. Okay. Now you must understand that two diodes must be conducting for voltage to be seen at the output. Again, two diodes must be conducting for there to be voltage at the output, right? Sure. So now let's see. Let's move on. Let's see what's happening here. All right. Now let's see here, and here, right? What's happening? You can see that 1 and 2 are on, so they'll be voltage at the output here, right? So that's like this A and C. So this will become VAC. Now, when I take this region here, it's not drawn to scale, so just follow. When I take this region here, B and C, so I have it like this. For this region, I have BBC. Then now here I have what? Here I have. Yeah, so let me go to the main drawing. Hmm. Papa, where is the slides? The slides. Hey, I'm pooping everything. It's not this. Papa, it's not this. Papa, it's not this.
Check. Hey.
Yeah, so we spoke about single filter last time, so let's move on. Sure. Yes, I was saying that I'm kindly hold. Okay, I'm coming. I'm looking for. All right. So yes, this is what I was talking about. So I was saying that was. I'm coming, please. Yeah. So here, as you can see, this is A. 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 Right. So A is on here. A is on here, and then D2 is here. Right. So that's from C. This is C. So I'm having VAC here. When I take here, I'm having what? When I take here, I'm having B and C. So VBC. When I take here, I'm having what? B and A. So here will give me VBA, and so on and so forth. Does it make sense? So that's it. Now, let's see. So this is for the area that will be seen at the output. That is the area. So we know that. So we know that the voltage for any sine wave, the voltage seen is given by area. The mean voltage, mean voltage is given by area over period, right? So if I have this region here, the region at the like the DC output, this angle is 60 degrees here. This angle is 120. But understand that now they are now displaced 60 degrees from each other. You get it? So this is 60 from the mean point here. This is 60 here. Then this is 120 here. So 61. We know that the area is given by E over omega, right? Cos. Sorry, I'm coming. The area is equal to E over omega, right? Then multiplying cos of the small value minus cos of the big value here. You get it? So be kindly punch it for me. Calculator. And you must understand that now we are talking about three phase, right? You know three phase. Three phase. So you know that the the line value is given by what? It's root 3 times its phase value. Right, yes. But I'm coming. I'm punching it, so kindly hold. So yeah, so as I was saying that, so we put in the cos 60 here minus cos 120, then here line voltage, so root 3 times E. Then you divide by the period. The period is the period between this 120 here, which is 2 by 3 and then 60. Right? When you divide this one, you get this answer here. The calculation is not even important. You might just know that, oh, okay, for a three-phase system, without overlap, if we neglect overlap, right, it means that in the input supply, you see, I do this. Sorry. Okay. Now, if for the when I was drawing the source, I brought an inductor here like this, right? This inductor will bring the overlap, but then so here we are assuming there was no overlap. Okay, if there's no overlap, I'll get my V DC to be equal to 3 root 3 E over pi. As compared to the case of the single phase, where in single phase VDC is equal to 2 E over pi. You get it? So here you get 3 root 3 E over pi here. Now, at this point, I want us to just know the formulas because that's what matters. That's what matters. The questions are usually straightforward, so let's just know the formulas. Now, when there's overlap, we'll see how the waveform is affected. Now, your mean voltage becomes this 3 root 3 over E, 3 root 3 E over pi, right? Minus the voltage lost due to the overlap. So let's come here. Let's come here and see something here. Come in, okay, hold on. Hey. It's down, overlap is down. Yeah, so now when you introduce inputs in inductance like this, they'll cause the overlap, right? So now you see without the overlap, we're seeing that what the output voltage look like this. It was like this, right? This is what we're seeing, right? Let me yes, this is what we're seeing here. So this mean value is what we are seeing is equal to the 3 root 3 E over pi here. Okay, but now due to overlap, this area is lost here. This area is lost here. I flowing. So due to overlap, this area is lost here. I'm coming. So that area is what's accounted for by. So this will become minus 3 ID LS omega over pi. There is a derivation. That's not what matters. It's not important. Let's just memorize the formula. Because like this is no time, so we can get to solve the question. So like as we are solving the questions, I'll make sure that like I explain the questions very well so that we know how they're coming about. Okay. So if there's overlap, this is what the output voltage becomes. So if there's overlap, then you realize that, oh, okay, due to overlap, then instead of the voltage looking like this, it will cut a portion of it out. So it will look like this. And this voltage will be seen across the inductor. So that's what happens. This voltage that's cut off, where does it go to? It comes here. It will be a voltage drop here. It will be seen as the voltage drop here. Yes. So it's like when there is overlap, here's what happens. See, when there's overlap here, when there's overlap, it means that what? It means that there's an inductor, right? You know that inductor doesn't make currents change in them instantly. So when there is a change over, the voltage at this point when there's inductance and at this point will be the same. So it's like this point becomes like a short circuit here. You get it? So now I can now move through this path here, and there'll be a voltage drop along the inductances. And that voltage drop is what is seen as the drop in the output voltage here. So this one is to be equal to 3 root 3 E over pi, then minus the drop due to the inductances, the finite input inductances. Sure. So that's what we'll have. Now let's see something again. I'm coming. Sure. Let's move on. Now let's see what happens to the DC current. But the laptop is acting very slow. I don't know why. Sure. Now let's take this phase A. Let's take phase A. Okay. Let's take the current supplied by the phase A like this, which is this one here. This is the voltage here. And you can see that okay, when the diode is on here, when D1 is on, it means that there will be current flowing through the source A, right? Which is equal to diode current. So you can see here, diode current plus ID. And it spans from, let's say this is 0, 30, 60, 90, 120, 150, 180. So here it is from 30 to 150. That's 120. So the angle here is 120, as you can see here. 120 angular displacement. Now it goes off, right? This A current from source A goes off up to this point. So it's off. It's off because at this point D1 is conducting. Yes, A is connected between what? So we say that A was connected between 1 and 4. 1 and 4. So when 1 is conducting, then there'll be direct current through A. Yes. 1 will come and A will come and conduct A again. When A becomes minimum, that's when 4 conducts. So now it's minimum. So it's to carry negative current like this. So this is how the waveforms came about. You get it? Now A goes off. A becomes maximum at this point again. When A becomes max, D1 starts conducting. So it means that it will come here. So it's between this period and this period. It's not A that's conducting. So it's off like this. So this is the three-phase current. This is how it looks like. Right. Now we expect that if we are giving it a sinusoidal input voltage, then we expect ideally what we expect is we expect a sinusoidal current like this. We expect a sinusoidal current like this. But that's not the case, right? So we say that, oh, then we are not getting the ideal case, which is a sinusoid, but we are getting what? This is a square wave. It's called a quasi square wave. This is a quasi square wave, right? So this quasi square wave, we know that from Fourier transform, we can approximate any wave as a sum of sine waves with integral multiples of the frequencies, right? So here, this is said to have harmonics. Like it's not a perfect sine wave; it's a quasi square wave with harmonics. So there are harmonics in this square wave. Okay, so now this brings us to some terminologies called power quality factors, right? Like a measure of how close our output is to the ideal case. Does it make sense? So that we say that we want to approach a sinusoid, right? But we are getting the quasi square wave. So I want to measure how closely they are related. So now this brings us like our first term called the distortion factor. Psi. So because we are not getting a sine wave, then this wave we are getting is distorted. Like it's not a sine wave, right? So it's distorted. Yes, it's distorted from the ideal case that we expect. So now this psi is given by the RMS of the fundamental. RMS of the fundamental over total RMS. Please, did we speak about okay, that's on its own. Kindly open it. Kindly hold, I'm coming. So over total RMS of all the harmonics. Total RMS of all the harmonics. Now, the next quantity is something we call the total harmonic distortion. It's given by 1 over this value you find here squared minus 1. Minus 1 here. Now, when we take numerical examples, we understand how these things work. So let's just follow. Now, we also have another thing called the distortion factor. That's by cos alpha, where alpha is the angular displacement between the voltage and the current. Okay. Then we have the last thing called the power factor, given by psi times displacement factor. This displacement factor, sorry, this distortion factor psi, this displacement factor, then this power factor, this total harmonic distortion. Total harmonic distortion. Okay. Now, what have we learned so far? We've seen how to draw the circuit diagram, right? And we've seen how to calculate the mean DC voltage. The mean DC voltage, which is this, without overlap. And we say that overlap would subtract or reduce it by this much. This much. If there's no overlap, means that there's no, this L is not here, so this is not here. So you need to make this one equal to 0. Yes. They're open code blocks. Alright. So we have it like this. Now we've also seen that, we've also seen that the output current, the current flowing through the load is not sine wave as we expect, but it's rather like this, quasi square like this. And this angle here is 120 degrees. We'll see what this angle is. And then we say that it's made up of harmonics, right? So this value is plus ID. This value is minus ID. And we say because it's not a sine wave and it's a square wave, it has harmonics present. Now let's see how to calculate the current, the integral components of the harmonics. So let's say so for any nth harmonic current, component of this quasi square wave, I'm getting 4. The formula is a formula. Just memorize it. 4ID over n pi. This is a peak value. Okay. Sine n theta over 2. Sine n theta over 2. That will be running slow. Okay. That will be running very slow. Papa. 3 is that was running very, very slow.
I can hear it from here, so fantastic.
Sure. Maybe you didn't.
If you didn't close
Sure. So now for this current flowing in the 3-phase diode bridge rectifier here, we can find we see that this theta here is this 120 here. So here it can become 4ID over n pi sine n times 120 over 2, that's sine n times 60 times 60n. So we have it like this. Now, you see, we said that the distortion factor here is what? I1 RMS over I total RMS, right? Of all the harmonics. So let's find I1 RMS from this formula. So from this formula, I1 RMS is given by what? 4ID over n is 1 pi. But RMS, this is peak, so divide by root 2. Sine n is 1, so sine 60. We divide this whole thing by root 2, so it's like the root 2 can be multiplied or added down. So now sine 60 is what, root 3 over 2. So now just calculate this whole thing here. So when you calculate this whole thing, you get what? 4ID over pi root 2 sine 60. Yeah. So this times 4 over root 2. So here, what are you getting? Theta is 120, right? So here is 60, n is 1. So I'm having this, yes. So I'm getting 4 over root 2 times sine 60. Come again. Come again. Yeah. Anything. Okay, can I do the peak? Show the peak value. Sure. Yeah, so that's it. Sure. Alright. So now this is the I1 RMS. Okay. Now for a three-phase system, the total RMS of all the harmonics here is given by ID. Okay, there's supposed to be my ID here. ID times square root of 2 over 3. Just keep it in your mind. That is the total RMS for a three-phase system. When we are doing three-phase, so now let me find my psi. So my psi will be given by root 6 over pi ID divided by ID square root of 2 over 3. Right? So psi is given by root 6 over pi ID all over what? ID square root of 2 over 3. So kindly do this. Do square root of 6 over pi over square root of 2 over 3. 0.9549. If you remember, the distortion factor for the three phase given by 0.9549. And this is for three phase. This is for three phase. Let's compare to the single phase. Single phase, we saw the single phase, that one, the current waveform is like this. It was like this. If you remember. And the displacement was 180 degrees. So that one my theta. So if I'm using the same formula, In is given by 4ID over n pi sine, this time the theta is 180 over 290, so sine 90n. So if I want to find I1 RMS, it's given by what? 4ID over pi RMS, so root 2 sine 90. This will give me 4ID over n root 2, pi root 2. Then for single phase, the I total RMS. So we are just using this formula. I1 RMS, that's the fundamental RMS over the total RMS of all the harmonic components. So I total RMS will be equal to I total RMS is equal to ID. Single phase equal to ID. So you must know this thing that for three phase, I total RMS is ID square root of 2 over 3. For single phase is ID. So therefore, my psi will be equal to this 4ID over pi root 2 divided by ID. And if you do this correctly, you get 0.9. So if you do what? 4 over pi root 2. Yeah. 4 over pi root 2. You get 0.9. Yeah. So for single phase, the distortion factor that's given by is 0.9. And once you have distortion factor, you can find total harmonic distortion. That's square root of 1 over psi squared minus 1. I think here is 0.301 or something. I'm not sure. I've forgotten. Then here too, same thing. Just use the formula to get what they are. So this is how you calculate the distortion factors. The power factor quality, the power quality issue component. So we have the distortion factor, the total harmonic distortion. If they give us the angle between the current and voltage, we can also find the displacement factor, and we can find the power factor. Sure. Please, they wait for me. Like, just understand how it works. Like, it makes analysis easy. Because we'll see a question. We'll see how what I mean by that. So now we've seen that the DC is given by 3 root 3e over pi minus. So you can just learn this one. Just learn this. So that if there's no overlap, you just take this component out. Now let's see. Alright, so that's it. So this is the mean DC voltage. We also seen that, oh, okay. Seen that the current going through it is quasi square like this with a displacement of 120. And we've seen that 120 seen that the harmonic components are given by this. So yeah, because it's 120 to become 60 here. Then psi is given by I1 RMS. So here, let me make here RMS. So you just learn usually we use that RMS usually. Just learn RMS like this. Then for three phase, then the psi is this over I total RMS. Then the I total RMS root of 2 over 3. So we evaluate this for the fundamental divide. And for three phase, you get the psi to be 0.9549. 0.9549. That's it. That's it. Now, we also know that for single phase, we saw that for single phase, we saw this formula that 2ID, check the sound. 2ID LS is equal to what? To find the overlap angle, it's equal to E over omega 1 minus cos mu. We saw that, right? So that, okay, there will be some overlap angle here. Instead of all these being parts, no, this part will be cut off. So okay, there's some overlap angle mu, right? And then this thing spans pi 180, so pi. So if you put it in the area formula, I explained all this in the other video, so you can get it from there. But in this case, in three phase R2 ID LS given by three phase, right? Three phase. So the E becomes what? Root 3E line over omega. Same thing. 1 minus cos mu. So to calculate the overlap angle in three phase, the only thing that changes is here. That here becomes root 3E over omega. But it's the same as this. 2 IDLS. The same as this. So you make your mu the subject here. You make your mu the subject and you find it. Can you hold, okay? So we are going to solve some examples, okay? So I'm checking the example we saw in the last video so that I don't know how to resolve them. So kindly stay with me. Okay. But we've seen this formula here. We've seen all these things. You've seen all these things. So kindly take time to read the effect of overlap. The effect that's a number. The effect of overlap, we saw this formula here already. I've mentioned this formula already. We've seen this equation due to overlap already. Eh, okay, so we solved. Oh, okay. So we've done example on the single phase ones. So we've done these examples too. It's left with the three phase. Lift it. Hello, hello. You're reconnected. Come on, finish. Ah, what is going on? The thing is plugged in, it's showing, but see no, we're stream. It's coming from the All right, please. Let's look at the next question. Papa, check if we saw this question. We saw this question. The other video. All right, let's move on. I'll get mine. All right, let's move on. Yeah, no. Actually. All right, say a three-phase rectifier feeds a smooth current of 100 amps to a load on a DC side. Ignoring the effects of overlap, determine the RMS fundamental current. So we know that RMS fundamental current I1. Check if it's coming in. I1 is what? We know we're using 4ID over I root 2 sine. This three phase. I think about sine 60. That's what you do. Then we said that the total RMS current is given by total RMS. We know that total RMS is I total RMS is equal to for three phase ID square root of, come and pay attention, 2 over 3. So we use that. Then find the distortion factor, find your total harmonic distortion, yes. Now number 5. A three-phase diode rectifier is fed from a 415 volt AC supply and provides a smooth current at 50 hertz, at 50 amps on the DC side. Overlap can be ignored, so we should ignore overlap. By considering the AC current, calculate the power that is drawn from the AC side. So there's an AC side like this. I think a rectifier. You're getting DC here. Right. So calculate the power that is drawn from the AC side. So we know that what P is equal to IV. right? P is equal to Ivan. P is equal to Ivan. So we have to find this. This V is already in RMS, so I have that V already. Fine. So I have to find I, right, and multiply them. This I here corresponds to the fundamental RMS current. So let's see. So it corresponds to the fundamental RMS current here. And we know how to find that one already. Right? We know how to find that one already. Using the 4ID over n pi root 2 times sine 60, right? Yes. So we don't want to find the RMS current and multiply by the VRMS, which we know as 415. Okay, to get it. But 3 phase, so root 3. So P is equal to root 3 V L I L. Now we have this side. Now the question says that okay, now also compute the DC side to also check if you get the same power. Because we know that for power converters, like if they're ideal, then P out is equal to P in. So let's find our P out too. That's a PDC. PDC. So PDC, we know what PDC we need. What we need. PDC is given by what? VDC times IDC, right? So I know my IDC already. That is drawing 550 amps. So I have to find VDC. When that VDC mean is given by what? Yeah, 3 root 3 E over pi. No overlap. So this. So use this formula to compute the VDC here. So that's what was done here, right? And then multiply by the outputs. You say when the current you get is the same as it's almost the same as this current. And now you see the formula. We need the formula to be what? 3 root 3 E over pi. Right? This E here is peak value. It's peak value here. But always the values they give us are RMS values. So now when I give me RMS, the formula will become 3 root 2 V supply, like that's the RMS over pi. Pick it RMS over root 2. Right. So pick it RMS times. So this is 3 root 3 E. 3 root 3 E over pi. Right? So we know that okay, we're having 3 root 3. We know that was E is what? E is phase voltage. No, E is RMS root 2. So this is V supply times root 2, right? And then usually the V they give me is line voltage. So you divide by what? Root 3. You get it? So this will cancel this. That's why we come and get the 3 root 2 times supply voltage. Alright. So that's it. So that's it for the 3 phase. Now the thyristors. The thyristors. Please take time and read the thyristors part. But you must know that the thyristors have the same equations as the 3-phase diode bridges, except that there is something called a delay of firing angle. Like you see with the diode, when it becomes forward bias, it conducts. With reverse bias, it goes off. With a thyristor, when it becomes forward biased, right, you must now give it a gate current. You must like activate it again before it will come on. So when you activate it, it takes some time before it comes on. That's what we call a delay angle called alpha. So you see how we saw for the three phase, for single phase, let's take single phase, right? So that was our VDC is what? Our VDC is 2e over pi minus what? 2id ls omega over pi, right? For Thyristor, it becomes 2e over pi cos alpha minus 2id ls omega over pi. You get it? Now, where we say that, oh, your overlap angle is, we know that, okay, 2id ls is equal to what? E over omega 1 minus cos mu, right? Now, here in today's Thyristor, this is diode bridge. So here you have 2id ls, right? Is equal to E over omega. Here it was 1 because it was like cos 0 because it starts from here. It starts from here. So that's like cos 0. Now, in the Thyristor, we say it starts after alpha. So it's delayed by alpha. So here it's supposed to be like cos alpha, not cos 0, minus cos alpha plus mu. So this is the difference. So this is the comparison between them. So you can just learn the Thyristor formula and know that for the diode, alpha is 0. So this will go away. This will go away. This will become 0 too. And to look like this. Can you see? Yeah. So this for single phase. Now let's take three phase. Same thing. You know that for diode bridge, three phase is what? It's 3 root 3e over pi, right? Minus 3id ls omega over pi. Here it is same thing, 3 root 3e over pi cos alpha minus 3id ls omega over pi. Then our 2id ls is equal to what? E over omega 1 root 3e 1 minus cos mu, right? Then here I'm having same IDLS is equal to root 3 e over omega cos alpha minus cos alpha plus mu. Yes, so that's it. So now we've seen the three phase direct rectifiers. We've also seen the Thyristor. So read, like, see, there are some reading things, but right now this is like what we need to be able to answer all the questions we have. Okay. Yes. So this is it for the Thyristors. Yeah. So please, we'll end here. So in the evening, we'll solve the questions under this, the Thyristors, and then we'll start in 5. Okay. So by tomorrow, we should be done with that. We'll just start solving the questions we have, like all the questions we have. All right. Thank you very much.